Alright, now we're getting into the good stuff. So why do electrons flow from anode to cathode? Also, why do electrons flow? This has to do with a lot of different things. This has to do with the potential across a cell membrane in biology and how that makes some things go across membranes for different signaling and communication between cells. The most important that I can think of is neurons firing. So neurons in our brain, in our nervous system, down our spinal cord, all throughout our body, fire because we have a difference in the potential of one place, which is across a membrane, and another place, which is the other side of the membrane. So inside or outside of the membrane, if there's a difference in charge, those electrons will want to flow in one side or the other, causing that cell to fire, or that neuron to fire. Okay? This is a little bit different. This is like a battery example, but it's really the exact same thing. So potential energy for electrons is higher at the anode than it is at the cathode. So all things move to achieve a state of lower potential energy, more energetically stable. So a rock will naturally fall under the influence of gravity to obtain a lower gravitational potential energy. So let's look at this from a kinematics point of view. So if we have gravitational potential energy, we can look at the potential energy to explain voltage. So if we apply a force to this ball here on a string with this person on a cliff, we have to oppose the force of gravity and the mass to pull the ball up. Okay? So that requires energy, or that requires energy to do the work, to pull something up using a force over a distance. Now, the total work that has been done is now the potential energy of that ball. This ball has potential energy. It has the potential to be kinetic, the potential to move down due to its position in respect to gravity. So now let's look at electric potential energy and the potential difference, which is voltage. So volts, batteries have volts, which is a change in potential energy measured in joules over a charge in coulombs. So one electron has a negative 1.6 times 10 to the 19 coulombic charge. So this many electrons, 6.25 times 10 to the 18 electrons, contain negative 1 coulombs of charge. So the key here is that a change in voltage is equal to a change in potential energy over a charge. So let's put our analogy together with the actual potential energy of the electric potential energy and the potential difference. So the potential difference is a change in the voltage, is a change in the potential energy per unit charge. Potential energy increases as electrons move from the cathode here to the anode. This shift in position goes against nature because electrons spontaneously flow from the anode to the cathode. So this is just an analogy to help you understand what voltage is. Because we couldn't actually put a little person on a wire and ask him to do this for you. So now, at the cathode, the electrons possess less potential energy than they do at the anode, as the electrons spontaneously flow from here to here. So if we look at this system in terms of building potential energy, we could imagine a little man pulling the electrons from the cathode to the anode. When those electrons get to the anode, they have reached their maximum potential energy. Then if we drop those electrons, it would be equal to 2 coulombs of charge from the anode to the cathode. Okay? So 24 joules of potential energy would be converted into kinetic energy. It would give us, and this would give us 12 volts, because we have if we have 2 coulombs of charge and 24 volts, well, 24 divided by 2 is 12. I think I said 24 volts. I meant 24 joules. All right. So, one more thing. The amount of energy per charge is constant, no matter how many electrons go through the wire. That's a key point. So the amount of energy per charge is constant, no matter how many electrons go through the wire. All right, so let's look at voltage again. Voltage, energy per unit charge. You won't be asked to define voltage on the AP exam, but we use voltage, so we want to know what it is. So the energy here is the difference between the potential energy of the anode and the cathode. The charge of the electrons, each carrying this number, I've already gone over. In a 12-volt battery, the difference in the potential energy between the anode and the cathode is 12 joules per coulomb of charge. If we were to take this many electrons at the cathode and drag them to the anode, it would require work. 12 joules of potential energy is converted into kinetic energy that we can use to turn on lights, start cars, that move this many electrons from the anode to cathode in a 12-volt battery. All right, a couple more concepts here. Potential difference. Potential difference is also known as the electromotive force. It's a force that causes electrons to move. We also have the standard electromotive force, which is standard states, 25 degrees Celsius, 1 molar concentrations, or 1 atmosphere if we have partial pressures of reactants and products. Those are the conditions that are in place for a force that causes electrons to move. Okay? It's also known as a cell potential or a standard cell potential. This is what we will be using here. Okay? And cell voltage is a unit for all of these is the volt. Okay? V. And we're going to be talking about cell potentials, standard cell potentials next. Standard conditions, 1 molar concentrations, 1 atmosphere, 25 degrees Celsius for standard cells. All right. Now, standard reduction potentials. So this is a big line of thought here. We've talked about voltage and how that is a potential energy difference over a unit of charge. Now we're talking about the reduction potential. So the gain of electrons and the voltage associated with the gain of electrons from a cation to its solid state. So these are standard states based on standard values, voltages, based on the standard conditions. So you will be given a table like this on the AP exam. Okay? And scientists, chemists arbitrarily said that the reduction of hydrogen was 0 volts. Okay? So anything down here has a negative reduction potential, and those that are above here have a positive reduction potential. Okay? There's also a more complete list of these in your textbook. And these are all reduction potentials, but in order to have the oxidation all you need to do is reverse the sign. All right. So reduction half potentials have an increasing ability to attract electrons. Okay, an increasing ability to attract electrons. So silver has a high ability to attract electrons. That potential energy difference is positive from the anode to the cathode. Okay, aluminum isn't interested in these electrons. Aluminum is stable as an ion, so it's that potential energy difference is negative from the anode to the cathode. So, which species will be reduced? This is a big question that you might see. The species with the most positive, least negative reduction potential will be reduced, as it has the greatest ability to attract electrons. So this is a star, a unicorn, a pony concept right here. An electron can only decrease its potential energy by moving the species with the most positive, least negative reduction potential value. All right, standard cell potentials. This equation is not given to you on the AP exam, so I suggest you write this in your area where you're putting those equations that are not given to you. So the cathode is where reduction takes place. Anode is where the oxidation takes place. So the overall difference in the potential energy per unit charge between the anode from the cathode is the cathode standard reduction potential of the cathode minus the standard reduction potential of the anode. Take a second and read everything on this page. All right. So here's a question. What is the cell potential for a voltaic cell that has nickel at one electrode and copper at the other? The cells are kept in standard conditions. So here are the reduction potentials. So the half reaction for nickel must be changed here as this is the oxidation half reaction. So this means we must change the sign for its value of E. Okay? So here are our equations. A positive value for the standard cell potential means that the reaction is a thermodynamically favored process. So we can change the sign here and add, which is exactly what we've done. Because the cell potential must be a positive value. So if you get a negative cell potential value for the galvanic cell, you did something wrong. Okay? Because positive value means that it's a thermodynamically favored process. All right, let's take a look at this last one here. Determine the value of the standard cell potential for a voltaic cell operating on the reaction between silver, nitrate, and solid nickel. So we take the values from the table of reduction potentials, and silver is reduced because it has the more positive reduction potential. So we had to flip the sign for the nickel again, and add it together. Okay? So here is something that we might see, is that we do not, even though this is the balanced chemical equation, we do not double the value of the reduction potential, because if we double the number of electrons, we still have the same number of volts. Okay? So we don't change the values of the reduction potentials unless we change their signs. One more example problem.